Is 11 a.m. and we are here to talk about CoreOS a little bit. Thanks to everybody for joining. In the background here, we've got Mel, who's going to be helping out with coordinating questions and making sure that any comments that folks have coming inbound get over to me so that we can make sure that everything gets answered for folks. What we're going to be doing for the next hour is we're going to talk about CoreOS. And this is a little bit more of a meta discussion. This is going to be discussing what CoreOS actually is, where it falls in the marketplace, how it compares with some of the perceived competition that we have, and as well as how we compose a lot of the individual tools that we've built together into what folks think of as CoreOS. So to start out at the very, very beginning, what CoreOS is it's a Linux operating system. And this is going to be Linux as in the operating system created by Linus Torvalds in the 90s while he was a doctorate student. And what grew into one of the largest collaborative software projects in existence up to this point. So again, we've got this Linux operating system, or Linux OS. And the idea of CoreOS is that we wanted to distill things down to the most basic components. You know, everybody's probably seen our logo here. It's actually a riff on the kind of historic model of the Earth. You know, we wanted to get down to what the core of everything that we're working with is. So when you have a Linux distribution, historically, there's been a few different methods of actually building the distro and distributing it. And these are going to be things like an ISO image. It's going to be the full DVD or CD image that you distribute out to folks. And this, you used to go buy a book at the bookstore, and there'd be a CD in the back of it with a Linux distro under of choice, and then that book would talk you through installing the whole thing. And then as we've progressed over time, ISOs were still there, but then you started having a package manager to distribute all of the individual pieces of software in that Linux distro to all of the folks who wanted to use it. So examples of package managers are going to be Yast, Yum, apt, and then even Slackware and Gentoo and some of the more I wouldn't necessarily say less user-friendly, but they're geared more towards power users. Even those have package managers. And the idea is that you're distributing software that's already been compiled so that each user doesn't have to compile it from scratch. There are benefits to doing that as far as knowing where all of your individual software has come from and being able to tune it exactly to your workload and your hardware configuration. But in the case of CoreOS, we are distributing an entire disk image that one can use from an ISO to install, but that you can also just apply directly to a disk using a command like dd, or even kind of methods of untarring it and piping it directly into a physical device. But so we have this Linux operating system that has a lot of the individual components pulled out. You know, with those package managed Linux distros, what they will do is they will package all of open source. So they're going to package the Linux kernel and SSHD and some init system, if I can spell init correctly, and then other really important libraries that you're going to need, like glibc. And then they're also going to package things for you like the Python programming language, and we'll say HTTPD and the MySQL server. And you get all of these together in that Linux distribution. They're going to handle collecting all of this and making it available to you as a user. And what we said at CoreOS was, you know, your Linux distro might ship version Python 2.7, or they might ship HTTPD version 2.2, but not everybody wants to use those versions. So what can we do to make this easier in the long run? What can we do to really ensure that all of these things can be put together in a sensible fashion? And the answer up to this point has been, well, you download your own version of HTTPD 2.4, and then you compile that yourself. But that kind of reverts back in time to the era of everybody having to compile their own software and having the full understanding of doing that. And we thought there has to be some middle ground where you can both bring the pieces of software that you want to use and run those in such a way where they don't interact with the main operating system in a negative fashion. And the answer that we had to that was, rather than shipping all of this, what if we only shipped everything on this side of the line? And then we found some mechanism for you to contain all of these pieces of software that are relevant together. And the folks over at Google really pioneered this. In the mid-2000s, they created these ideas of Linux containerization in combination with folks from Parallels and SWSoft and developers on the project LXC. Parallels / SWSoft created back in the day a project called Virtuoso. And Virtuoso then became the parentage of a product called OpenVZ. And at the same time that they were working on OpenVZ, other individuals started developing the project LXC, and eventually these converged a bit and joined forces. Google contributed a lot of code to LXC, and what all of these are containerization systems. These are the primitives that then allow a distro like CoreOS or a technology like Docker to be able to put a number of pieces of software all together into one single namespaced entity and run those in a fashion that's not going to interact with the other pieces of software in a way that you don't necessarily intend to. Now I can spin up one container that's running Python 2.7 and HTTPD 2.2, and I can spin up another container that's running Python 2.6 because I have an older application that has a dependency on that, and at the same time a newer version of Apache where this one is running 2.4. This all becomes possible in an era of containerization. So bringing this all into things that are a bit more useful here, we now have this Linux distro where we're packaging much, much fewer things. But now you need some method of actually executing all of those individual containers. And you need some method of actually transferring them down to your computer directly. So the answer to that is in one of two forms. One, you have Docker, where Docker is a containerization mechanism that also provides the transport for searching and finding all of these individual containers. You can use Docker to find your Postgres container, or your HTTPD executor, or even something that's just a very, very small execution engine, like the one that I've built called CoreBox, where CoreBox is a container that it's approximately 7 megabytes that has glibc and everything else that you would need to bring in another statically compiled binary or something that is been, it works wonderful as a development environment for compiling your own pieces of software and including them all together. So another option to this is things conforming to the application container interface specification. And those are going to be executors like, for example, Rocket, where Rocket is just one small piece to do all of the functions that Docker is attempting to do for you. So using Rocket, you can specify an HTTP endpoint where your Postgres container might run, and now use Rocket to download that and run that single small composable unit. Containerization gets you the ability to distribute these pieces of software in a very easy fashion. But there are a lot of other problems that need to be solved. When you have a traditional application, you might want to run 3 copies of it. And then as you start becoming more and more popular, you're going to want to add more nodes and then start load balancing all of them. Well, the first problem that you run into is configuration. How do you distribute configuration across all of those? And for many, many distros right now, the answer to that is a configuration management system like Puppet or Chef. But we thought, what would happen if you could take your etc directory and distribute it around the entire cluster in such a fashion where any of the values that you write into it get replicated in a fault-tolerant manner so that you can quickly recover from nodes which are getting lost. That's the whole idea behind etcd. Now, etcd has found additional use in also being a lock manager as well. So now, when you have all of these machines that are running different versions of software, so in this case, I've got, out of my 7 total nodes, I've got 3 that are running the newer 2.0 version of my software and 4 that are running the older 1.0. With etcd, you can now take a lock on an entire cluster to say, this machine wants to go down for reboot, and bleed all of the traffic away from that one single node, and then perform the update that you happen to need. This also allows you to, in the event of that catastrophic failure, let everything else in the cluster know the state of where that lock was when the host went down, and given a reasonable time to live, react to the fact that the host is no longer available. So using that lock mechanism, now when this host comes back online running version 2.0, it can release the lock and allow another host to take a new lock. So now you can do a rolling update throughout the entire cluster, one node at a time, giving you the ability to have a reasonable service window without having that specific logic built directly into your applications. So what CoreOS is, to reiterate, is we have a Linux distribution that's using containerization along with etcd, which is a configuration system, that also handles locking. Now that we've got these steps, the next problem that you run into is, as you keep getting bigger and bigger, you want to treat all of your hosts as just a general compute resource. You want to be able to say, I need to deploy 3 copies of my web service, but I don't want to care about any of who these individual systems actually are. I don't want to worry about, per se, that this one is in rack 1 and this one is in rack 3. I just want to be able to say, here's a service that I want to run, and this pool of compute needs to run it. The tool that we use, that we have written to solve that problem, is called Fleet. And what Fleet does is it takes this definition of a service, stores it in etcd so that all of the members of the cluster have access to it, and now the Fleet daemon running on each of the boxes shares the state of the running application into the cluster so that all of the other nodes can figure out how to work with that and make a decision as to who should run that service. So given that I have my Web 1, Web 2, and Web 3 services, I can store these inside of Fleet, which, by the way, uses etcd for that transport mechanism. And now say, cluster of machines, please run Web 1, run Web 2, and run Web 3 for me. And the machines themselves will decide where Web 1, where Web 2, and where Web 3 happen or are actually executed. Using those same failover mechanisms that we leveraged in etcd, if for some example or some reason the node running Web 3 goes down, the rest of the members of the cluster can detect that that service is no longer running and reschedule it on another machine. Fleet allows you to build fault tolerance in such a way where, again, the applications don't directly need to know how to make all of this work. They can just be scheduled upon some compute resource, and all of the underlying components make sure that that service stays up and running. So we've got Linux, we've got this containerization system, we've got etcd, we've got Fleet. The next problem that we saw in this is that when you are scheduling these things to run around a cluster, with incumbent containerization systems, they perform port mapping for you, meaning that they only expect each individual machine to have one public-facing IP address, and then they perform network address translation, or NAT, behind this, and they create a virtual network bridge, which all of the containers inside of a single host will actually sit on that bridge and have their IP addresses natted behind that single publicly available address. This introduces a lot of problems when you're trying to note both the host name and the actual port number that an application is running on. These Web 1, Web 2, and Web 3 applications, they all expect to be running on port 8080, because that's what their application server, in this case, we'll say Unicorn, is designed to be running on. But for each of these, despite the fact that they're all listening on 8080, with the actual host itself, that might be presenting itself as port 49123, 49124, sorry, say 49153, make this fully RFC compliant, and 49155. Now I need to again know the specific port number that one of these containers is running on, rather than recognizing that it's merely running on 8080. The tool that we use to solve this problem is called flannel. And what flannel does is it performs a UDP encapsulation between two hosts to make it so that hosts all residing on that shared bridge interface, that all of their containers can see each other very cleanly without having to know specifically what host it's on. So how this works in a more technical fashion. Given that we have 3 hosts, flannel running on each host will take an RFC 1918 address space. This is going to be something like 192.168.1.0, and we'll say /22, which, by the way, that means that this is going to be 192.168.1.0, .1.1.2, and .3 /24 are all going to be contained inside of these. This /22 references these /24 addresses. And then we'll take one of these and assign it to each one of the hosts. So now this entire network, 192.168.1.0/24, all exists inside of that machine. 192.168.1.1/24, 192.168.1.2/24. And what we're really creating here is this flat network where a subnet of each of those exists on each host, and now a container running on this host right here, and we'll say that this is container running 192.168.1.50, sorry, .2.50. And a container running over here, which would be, we'll say that this is our web container and this is our database container. This database container is going to be on 192.168.1.75. And since it's running Postgres, it can bind directly to port 5432. And now this web container can look up in etcd, figure out that the database container is operating directly on that IP address, and can know that it's expecting to talk to a Postgres container and directly talk to it. And what's happening is that this web container is talking to the flannel interface. The flannel interface encapsulates that into a UDP packet that's destined for the other host. Flannel on the other host then takes and removes that out of UDP and creates it back as a TCP connection destined for this individual host. We can now have this mechanism where this entire network, all of those addresses can be directly seen by each other without having to worry about the mapping of the individual addresses that was occurring with NAT. Now, this still requires you to expose the very endpoints that you plan on having end customers talk to on some known address, so that you can then put it behind some kind of a TCP reverse proxy or some load balancing software. But it makes the interconnection between containers much more simple. Now I can have additional copies of web all running around the individual cluster. And if I move a container from one host to another, it knows that it can still talk to that address right there and doesn't need to actually remap. Take a moment here. I'm going to grab a glass of water. Does anybody have any questions? There's a Q&A module built into the Hangout. Feel free to type any questions into that. And then as they come up, we will kind of address all of them and make sure that everybody at home is following along. So like I say, give me 1 second to clean up the whiteboard a little bit. Grab a drink of water. Give me 1 second here to take a look at my notes. So I started to mention that we have these disk images and that we commit them down to an actual disk. And this is a good segue to talk about how CoreOS is actually residing on the disk of a machine. So given that we have, we'll say, a physical machine with one disk in it, this disk would normally enumerate within Linux as dev SDA. This is going to be referring to the first or alpha SCSI device on that SCSI interface. So we've got dev SDA. And then blowing this up a bit further, what's going to happen under the hood is that we're going to carve this into a number of smaller partitions. So we're going to have an EFI partition.
We've gotten a couple of questions.
Okay. So go ahead and acknowledge one and read off the first question.
Okay. Is Flannel using RFC 3948 style UDP encapsulation or something fancier or newer?
My guess is that it's going to be using RFC compliant, or the first thing mentioned. I don't know the exact mechanism that's used behind it. Our lead developer on that, Eugene, has done a lot of documentation. So if you were to go to github.com/CoreOS/flannel, there's going to be a documentation directory inside of that goes over the more of the details of it. Additionally, on top of that, if you have any other questions after this meetup is done, if you were to go to #CoreOS on Freenode. Freenode is an IRC network. #CoreOS is where most of our developers and engineers actually interface with the community at large. So that's a great place to get questions answered as well.
And then the next one, how do you handle database failure? For example, if you have a Postgres container in a node that crashes.
So that gets to one of the bigger issues right now with containerization. And that is less the problem of the database directly, but more the problem of how a lot of databases are built and the problem of replicating disk state across a number of machines. So Postgres expects, by default, all of its files to live in var lib pgsql. And Postgres itself is not doing anything to actually replicate the contents of that directory across to other nodes. There are some options that you can do to make that occur by, for example, putting the contents of that directory on top of a Ceph or a gluster.fs volume. But both of those are going to incur a performance hit. This is where a lot of newer databases really shine. For example, the database Cassandra, the database type cockroach, and from the folks over at Percona, MySQL Galera. Each of those database types actually replicates the contents of those folders to other hosts as well, to act in a way that's more tolerant of failure than a database like MySQL or Postgres just running by itself on a single host. As of now, storage is a known problem. It's what we refer to as kind of the WordPress issue. It's you have a piece of software that was never designed to run in a containerized environment. It was also never designed to run in a highly available environment. That is to say, it's not separating out state of a user from the core application components. So my session information isn't stored in a caching server that can replicate across a number of hosts, so that if my session, for example, moves from one host to another, a new web worker can handle that cleanly. The same types of problems exist with databases, and that is something where we are still looking towards the community to see what the right answer for that is going to be in the long term. Any other question?
No.
Okay. Then what we will do is we will move back on to a discussion about the partition layout. So as we mentioned, inside the disk, we're cutting things up into a number of smaller partitions. The first of those is going to be the EFI partition. The second one, which is much smaller, is going to be the BIOS partition. And what's happening here is that the EFI partition is where the bootloader is actually living. And then that bootloader has a small secondary partition so that legacy hosts that only have a BIOS and don't have EFI on them have some mechanism for falling, like getting a hint as to where the EFI partition actually is. All that this actually does is has a very small kernel and bootloader, which are then used to then choose one of the main partitions. So we have two primary partitions that exist on the host. One is going to be called user A. The other is going to be called user B. We'll come back to these in a minute. On top of that, you have a couple of what we call OEM partitions. And then finally, we have one large partition called root, which is your data partition. So the actual boundaries of every one of these partitions, with the exception of root, are set in stone. They're, in a way, the CoreOS version of Bill Gates's famous 640K number. You know, they're arbitrary boundaries that we picked, that we decided to stay inside of as a distribution. The reason being now, we can always make an informed decision as to which partition we're actually talking to, just again, by partition geometry. The reason that this one partition root does not follow that same standard is because we make that the last partition, and then we have a job that will run on boot that expands that partition to the end of the physical geometry of the disk. That means that if I have this image that we'll say for 5 gigabytes, and then I apply that to a DigitalOcean server, which has a total 20 gigabyte disk size, this partition will then expand to fill that entire 20 gigabytes or the remainder of it without changing the actual location of any of the rest of those partitions. So the root partition is where all of the content that you write to that host is actually going to live. It's where all of your containers are going to be, any changes that you make to the configuration, any temporary files that you store, etcd contents, they all go to that last partition called root. And that partition persists across boots. So if I write a file into temp called foo with the contents of bar, and I reboot that machine. Actually, let me say, if I write a file into var redbeard, and I put the text foo equals bar inside of that file /var/redbeard, and I reboot that host, when that host comes back online, that content is still going to be there. CoreOS works great for ephemeral workloads and for machines that you plan on quickly deploying and tearing down and deploying and tearing down. But it doesn't mean that just because you write files to the disk, they're not going to be there later. And that's an important distinction that we wanted to make, because just this week we were talking to a number of folks who were concerned about that. So it's a good opportunity for us to point that out and let you know that, if you have, a large number of disks in the machine, we've seen folks who have machines with 80 disks in them, and then they start carving that up for their particular workload. By doing that, all of the data on those disks will live in perpetuity until somebody actually removes it or BitRot gets it. But that first disk is what handles making sure that CoreOS stays online and running in a clean fashion. So, moving back up this stack a little bit, let's take the opportunity to talk about user A and user B. So, when you go and install CoreOS for the first time, it's going to create this partition layout, and it's going to place CoreOS in this user A partition. The first time that we publish an update that this host sees, it will download the full contents of that disk image. It will stage it to a location like temp, since it is going to be a temporary file on the disk. It's going to do GPG validation to make sure that that package was actually came from CoreOS, that it was signed by us, and that you can trust that it hasn't been modified in flight. The NSA hasn't gotten in and weakened the encryption in that image just because, or during the time in which it came from the CDN down to your local machine. And after we do the GPG validation, we can rest assured that nothing about it has actually changed. And then what we will do is we will start placing that file onto the user B partition. So we will start writing all of the contents of that down to this disk. And when it's done, we're going to get a message back that we send to dbus that tells the host that we need to do an update and that this is going to require a reboot. After dbus signals that, the machine is going to actually go down for reboot. And when it gets to this bootloader here, it's going to look at metadata on both of these partitions, and it will make a decision about which one to actually load from. If we go to load user B, it attempts to boot it, and if for some reason that user B partition does not load correctly, we know that we will be able to fall back to the known good partition that we were previously running from. That's going to be our user A partition. So ideally, we're going to boot this user B partition, and everything's going to work just fine. Assuming that that happens, we go ahead and we are running off of that. And the next time that there's an update that comes down, we'll again stage it to temp. We'll do validation of hash, date, and GPG signature. And then we would actually apply that update to the user A partition. Similarly, we would reboot loading off of user A. We would know that we had a running user B partition that we can always fall back to if there was a problem. Saying that there was, or assuming, just for argument's sake, that there was a problem with this user A partition, what'll happen is we reboot back, we're running off of user B, and then we're going to wait. The next time we see an update come through, we will attempt to apply it again to this user A partition. Write it down to the disk, reboot, attempt to run from it. And this time, now that we have a working, good update, we just keep running off of that, and then we'll stage the update and apply to the user B partition the next time. So we just keep pivoting back and forth between these two disks, these two partitions on this disk, to always guarantee that we have both a known good state and a clean path for upgrading in the future. This is how the updates inside of a CoreOS host actually work. We have the update, which comes down from our update servers, stage it to disk, validate to make sure it hasn't been modified in flight, and apply to disk. Now, additionally, we have these OEM partitions. The purpose of the OEM partition is just to store a small amount of data that is specific to the mechanism that you use to deploy the host. That means that in the case of VMware, we're going to be shipping the VMTools daemon on that partition, so that all of the other OEMs don't need to ship that software. You know, for example, if you're running on top of Rackspace, it really doesn't make sense to have the VMware tools shipping inside of that. And similarly, if you're running on top of Amazon, you really don't need any of the OpenStack tooling in there as well. So that gives us the ability to make a slight change to the state of that machine while still keeping the majority of the contents of what CoreOS is actually doing static and the same across all hosts. And this mechanism of guaranteeing that everything is the same is really important to us. In the process of deploying a CentOS machine, you're going to notice that when you deploy that to a physical machine, you'll use something. I should switch to a marker that everybody can see a little bit. In the process of deploying CentOS to a physical machine, you're going to use something like Kickstart to specify the manifest of what that machine should do on loading. If it's a physical machine, you're going to have to load via PXE or off of an ISO image and specify that. Well, at the same time, if you're deploying onto Amazon or GCE or Rackspace Cloud, you're going to have to specify a cloud config. And that now means that you have two incompatible manifests for specifying what a host is actually going to do, which means that your operations teams need to act differently whether they're planning for deploying in a local data center or whether they're planning to deploy to a public cloud. And that really struck us as being a suboptimal solution, which is why we unified on cloud configs as our deployment mechanism across the board. So you will have a definition which says config. And I will say host name is going to be redbeard.coreos.com. I will say add this user name redbeard UID 10,000. And while we never really suggest setting passwords in something like a cloud config, you should really, whenever possible, try to opt to use SSH keys instead. You can specify a password hash in this cloud config definition as well. So you'll notice that I've done *6 or $6 $salt and then my hash, because I really want to specify the most secure hash possible. Right now, with the version of glibc that we ship, the most secure hash is going to be a SHA-512 hash. So make sure that you use that rather than something just like salted MD5 or SHA-1, SHA-2. So using this, I can now have this manifest so that when I deploy 10,000 machines using this manifest, I can have this user deployed on every one. Now, ideally, something like hostname is not something that you're going to specify in the manifest. As much as possible, you're going to want to use things like DHCP to your advantage. There's a lot of really helpful features by using DHCP to deploy the systems, besides just IP address. One of the questions that we were asked about on a semi-regular basis is how I make configuration changes to a lot of machines at once. For legacy components that don't know how to query etcd to figure out what these answers are. And given the case of a lot of them, like the host name or the NTP address, all of those changes can actually be made in DHCP. Now, for some folks who are not running their own DHCP infrastructure, it means that you're going to have to rely on the cloud configs through the provider to set some more of those discrete options. But the only difference here is that this cloud config will only work really for configuring one machine, because it has some state-specific information stored inside of it. And now if I remove that out, this is something that is more generic, because I can rest assured that the only thing that this is going to do is create this user with a consistent UID and a consistent password on all hosts. Additionally, though, we've made a bunch of extensions to Cloud Init and Cloud Config files, so that we have our own namespace called CoreOS, and then I can specify units. So now I can go so far as to say, I want to run my monitoring service. And I want the command for it to do to be start. And then I can specify the content that I want this unit to perform an exec start, user bin rocket, run Datadog. And this will, in this case, I would specify the HTTP endpoint where my Datadog container is actually running. And now every host that's deployed with this cloud config will have the user redbeard created, again, with a consistent UID and a consistent password, and will run a copy of this monitoring container and retrieve it from the endpoint that I specify inside of this, do all of the validation that it needs, and make sure that it's all synced up back with my centralized monitoring. I'm going to take a second to grab another drink of water and give folks an opportunity to ask questions. I get the feeling that this is some questions coming inbound from IRC.
We do have some more questions.
Okay.
So, first question, what sort of monitoring service do you recommend for CoreOS? Traditional stuff like audit ID seems to not be ready for this container world.
So one of the things, as far as actual services, I don't generally use a lot of individual services like this. What I'll do is I'll stand up a combination of things like Logstash, like the Elk kind of platform. So Logstash, Kibana, and Elasticsearch to start to aggregate all the logs from an individual system. And then I will spin up an actual SNMPD container down here where I can have this container doing monitoring of the entire host to keep an eye on CPU, memory, etc. And then I can specify environment variables there that tell the SNMP container how to actually expose traps out to the network, while at the same time telling it that it should bind to port 514, 514 would be LDAP, port 169, I believe, for SNMPD, so that now any of the hosts that come online, the actual monitoring system that's like Nagios or something else that's collecting all of the data can look into where all of these hosts check into etcd. They know, because this is built into the cloud config, that every single host is going to be listening on port 169 for SNMPD, and can actively know that it should be involved in the pool of known machines that are going to be monitored. So that's one way that you can do it with open source software, so that you don't have to use a specific service. I just mentioned Datadog because I know that they've done a lot of work on their side around making sure that CoreOS and containers work as first-class citizens.
And then the next question, going back to network security, how about network security isn't UDP insecure?
UDP is not per se any more insecure than TCP, only you don't have a guarantee or a receipt of transmission, so you don't know if the sender doesn't know if packets were received on the remote side. But UDP is a lot faster. With Flannel, though, it's not something that you want to do across a firewall, just because there's going to be a small performance hit in encapsulating that traffic. So you want to make sure as much as possible that it's behind firewall, because then when you start getting into having packets encapsulated inside each other deeper and deeper, it can be confusing for some software to de-encapsulate it. That's one of the problems with SIP, session initiation protocol traffic, operating over a firewall or a NAT system. So when possible, you don't want to just have UDP traffic in the clear, or just like operating over the public internet for Flannel specifically, but there's no technical limitation as to why you can do it. And it does. There is a good point that there is no encryption on top of that, depending on the transport type. We are expanding into being able to provide more like VPN type interfaces as well for folks who do need encryption, but there isn't direct encryption in it because there are a lot of users who just wanted to be able to use raw VXLAN and just layer 2 technologies without going further up the OSI level.
That's all the questions right now.
Okay. So we have a cloud config file, which has specified things that we now want a number of hosts booting up to actually do. So the next thing that we should do is talk about how to deploy machines in an intelligent fashion. We're going to focus on cloud providers for a little bit here, but the ideas that we're expressing can easily be taken into your own data center. So first, let's discuss the idea of an availability zone, or an AZ. In the case of your own data center, if you were to have 3 availability zones, AZ1, AZ2, and AZ3, you don't want redundant components shared across an availability zone. This is going to be expressed more clearly in like, this will have backup generator, generator 1, and backup
I have to find a less squeaky marker.
So this is going to be router 1, switch 1, router 2, switch 2. And the idea is that you don't want a failure of any of these components to affect anything outside of this failure domain, this availability zone. And providers like Amazon, they give you these availability zones built in. So you might be able to say, I want all of these systems deployed in this specific region, but then within that region, I want to use different availability zones. And what that now means is that if I have 3 nodes running in availability zone 1, and I have 2 nodes running in availability zone 2, if there is an outage in availability zone 2, it's not going to affect any of the things in availability zone 1 unless it's a really catastrophic issue. Similarly, if I have 3 availability zones, AZ1, AZ2, and AZ3, and I set up 2 nodes in AZ1, 2 nodes in AZ2, and then a single node in AZ3, we'll say that these are all members of an etcd cluster. Now, if I have that same problem in availability zone 2, I've maintained quorum with this cluster across that without having to worry about anything else in the design and the placement of my individual hosts. when the issue is recovered in AZ2 and those hosts come back online, they can cleanly come back into that cluster and be brought up. While at the same time, if you then lost AZ3 or you then lost AZ1, any failure of a single availability zone guarantees that a majority of your infrastructure stays online. And these are the types of considerations that you want to make. You want to guarantee that you use things like availability zones to plan out the placement of your components. Speaking of placements, a common request that we get with etcd is that somebody sets up 2 nodes in Dulles, and they set up 3 nodes in San Francisco. We've got opposite sides of the United States. Pardon my. And what's happening here is that etcd is going to have to write information down to disk every time it actually receives a change to be made to its write-ahead log. So that means that there's going to be a lot of data going back and forth to that disk, and this is going to be one of the biggest things that you need to tune with guaranteeing that etcd is up and running in a really efficient, speedy manner. Now, if you've built your cluster in such a way where the nodes are split across a large geographic distance like this, it means that guaranteed on a round trip between those two, you're going to have a minimum of 150 milliseconds of latency. That means that every single write request that you go to put into either side of that is going to take a minimum of 150 milliseconds to return, because it's not going to acknowledge that that change has occurred in the cluster until a simple majority of the hosts have completed that change. And that means that if you're lucky and you make the change just over here, you'll probably be safe until you lose one of those nodes. And now if you've lost one of those nodes, what seemed like acceptable performance before is all going to go through the floor, because now you need to wait on one node from the opposite side of the country to confirm every single write that you do to that cluster. So now you're going to go from 8 millisecond response times on writing things to etcd into 158, solely because of the placement and that geographic distance that's in there. So a much better solution there is going to be to have smaller clusters of etcd machines in each location. And now, if one of those locations goes offline, you still have some other place that you can request the information from that's going to have that latency built in, but it's more predictable. And that also means that when you're planning out your clusters, if you give them consistent names, you can now use subdomains to make intelligent choices about which cluster you use. This is all basic tenets of service discovery and using CoreOS. Now, I know that all of this right here is going to be my search suffix within DNS. So I can say, I need you to talk to etcd 1, 2, or 3, and then let the host, the DNS resolver on that box, actually decide what the rest of that name is. Because now, by doing that, the software can get deployed the same into every one of these locations. By default, it's going to use its local infrastructure, And then if there's a problem, you can make a change so that core etcd 1, 2, and 3.coreos.com then point to specific infrastructure in one of those locations. So now a host can just make the assumption, oh, well, I'm in IAD, so I can fill that in to this string, and I will use the local components at Dulles. While at the same time, something that's deployed in SFO and another one that's deployed in DFW will all choose their local infrastructure. As these things are getting more complex, this is going to be something that I'm sure folks are going to have questions on. So, since we're kind of coming up on the tail end of the hour here, I want to give folks that chance to ask any more questions here, kind of get one-on-one time. And also, again, as soon as this is done, I'm going to be hopping on IRC, and I'll be on IRC in #CoreOS for a while. So if you have any questions at all and you want a little more interactive and we can share everybody's questions across the entire IRC room, we're going to be, this is on irc.freenode.net. This is going to be in the room #CoreOS, and my username is red_beard. So again, we were in the process of talking about basics of service discovery. So this is going to be using things like the DNS search suffix, using localized clusters of machines, and then utilizing the infrastructure inside of the overall DNS system to make these things simpler. Up to this point, one of the more common ways that folks have had for deploying an etcd cluster is use of a discovery URL. And discovery, that is going to be a URL that's generated for single-use deployment of a cluster off of the hostname http://discovery.etcd.io/new. And what that will do is that will generate a UUID and then provision that so that you can hand it to all the members of your cluster and they can then find each other. One of the exciting things coming in etcd 2.0, a feature that was written by a wonderful engineer from our team, Berke Mischner, who it's the use of SRV records for your discovery. So what this will actually look like is you would be able to specify _etcd-server._TCP in SRV 02379, and then we can say an actual host name. So we'll say caster.coreos.com. And what this is telling this is now anything that is looking for the server-to-server address on etcd, it can query this within whatever domain that actually exists on. And at a priority of 0, which is the highest priority that you can have, you should talk to port 2379 on the host caster.coreos.com. Similarly, you can have a second record where we say in SRV 02379 pollux.coreos.com. And now, through querying these DNS records, an application can get an idea of the entire topology of what that etcd server-to-server infrastructure looks like and find all of the nodes similar to how it would have done using the discovery URL. Additionally, we've added in support for client records as well. So you can have etcd client, CLIENT._TCP. And what we're expecting is that the official bindings that we're writing for etcd will understand all of this so that now an application can just say, I need to talk to etcd and utilize infrastructure like that to even handle the auto discovery, regardless of the type of network that it's deployed in, be that Amazon, private cloud, or even bare metal in a data center. We've covered a lot of information here. I thank everybody for coming out and listening to us talk and share information that we wanted to, let the community know about how CoreOS actually works. Again, that is the best mechanism for getting in touch with us and collaborating with us. Also, feel free to look through our GitHub repositories. Our organization name is CoreOS. So if you go to github.com/CoreOS, you'll find all of the various software projects that we're working on right now and find ways in which you can collaborate, contribute patches, make comments, and submit your own issues, because we'd love to hear all the feedback. Thanks so much, and we'll be talking to you soon.